So, yeah. Hello, everyone. Thank you so much for joining. So today we are delighted to introduce our session head seminar speaker. He's Sasha Plavin. And Sasha is a current fellow at the Black Hole Initiative. And he's currently focusing on observational studies of AGNs and blazars, and he works on multi-wavelength observations, so from radio, VLBI, and optical to neutrino. And he has done research on particle acceleration and many broad topics in astrophysics, including emission scattering. Sasha is a member of the KM3NED, which stands for Cubic Kilometer Neutrino Telescope, and also the Event Horizon Telescope collaborations. And as I mentioned, Sasha is currently a postdoctoral fellow at the Black Hole Initiative, and he completed his PhD in 2022 at the Lebedev Physical Institute in Moscow in Russia. And today he will talk about the ultra-high energy cosmic neutrino observed with KM3NED. So we're very happy that someone will run us through the astrophysical interpretation of these events. So thank you, Sasha, and take it away.
Yeah, thanks for introduction. Indeed, I'm happy to be here from a little bit down the road from the Black Hole Initiative. And today I'll talk about this ultra-high energy, the highest energy cosmic neutrino detected that was recently announced from the KM3NED collaboration. So just very briefly, what are the kind of relevant energies in the landscape of astrophysical neutrinos we are talking about and why they're interesting? So probably the most well-known astrophysical neutrinos come from supernovae. They are, for us, considered very low energy. They are like at megaelectron volts. These are the same processes, the same nuclear reactions as we can do on Earth. And I will only be talking about the highest energy neutrinos of teraelectron volts, petaelectron volts. At these energies, within the standard model, there is no other way to create these particles other than ultra-relativistic hadrons interacting with either with other hadrons or with photon fields. And after reproducing a pion, like some charged pion, this pion later decays and produces a high energy neutrino. This is effectively the only way. That's why we are always interested in astrophysics. We are always interested in the astrophysical context to detect these neutrinos, to observe them, because they are really the most direct evidence for hadronic processes in distant sources. Regarding in the past decade or so, or even more, about a decade, it brought a lot of advancement in the neutrino astronomy. So the first sources were AGNs and blazars in the well-known KXS 506 blazer in 2017. Then there was Milky Way a few years ago, our own galaxy. Potentially there are other sources, but they are just not, we are not certain about that yet. This means that like high this teraelectron volt neutrinos from the sky, they are already kind of detected, discovered. Most of these results come from IceCube. It started the earliest, almost, soon it will be 2 decades ago, it detected these neutrinos that could be associated with the sources. Specifically, the KM3NED is a younger telescope. It's water-based, unlike ice-based. IceCube. So, and the KM3NED is located near the detector itself. It's also located near the shore of Italy, southern Italy, in the Mediterranean. And it consists of these kind of like optical modules, optical multipliers that what they detect is with some flashes of light. This is a Cherenkov radiation from ultra-relativistic muons, and these muons are can be produced by neutrinos underwater or whenever they interact with something. Very rarely neutrinos are barely interactive with anything, but sometimes they produce muons, and these muons, the radiation of these muons is detected by these photomultipliers. Basically, all of these large high-energy neutrino detectors are built the same way, just KM3NED is underwater. There is also Baikal GVD Lake Baikal based on the same principle. IceCube uses, it's the same principle just under the Antarctic ice. So that's the setup. And KM3NED is the youngest. Younger than ice cube. And today I will be talking about this specific, like when this highest energy neutrino ever observed that Kepler was lucky to catch. And as I said, what these telescopes detect, they detect the inherent radiation of a muon. And here is this is a path of a muon, the reconstructed path of a muon, and this kind of the size of these blobs here, it represents how bright the signal was at each of the photodetectors, and the colors they represent time. So basically, how you construct the track is you see how bright is the signal everywhere, and at what point in time it came. So these are like on the kilometer or hundreds of meter scales, and you can really track the speed of light at these scales. So this is an event that is like even more energetic than was generally expected for many astrophysical neutrinos. It triggered like about a third of the photomultipliers in the whole detector, and it was as expected. It was a muon track. The signature was very indicative of a muon track, and it came from basically the horizon direction. This is exactly what is expected if we see neutrino at highest energies. We only expect to see from the horizon, because it cannot come from below the below the ground, because even neutrinos at these energies are absorbed by the Earth. And of course, it can come from above, but from above you see you have a lot of atmospheric background. So this is the direction is basically the only one that makes sense. It came from the horizon, and it was a very bright detection. This is the same kind of visualization. Just you can see the muon passing through the detector, and this cone is a light cone because the muon travels faster than the speed of light in the water. That's kind of the reason for Cherenkov radiation in the first place. So that's what the detector saw, and at these energies where you see like a third of your detector being light up, it's relatively easy to reconstruct the direction and be certain that it comes from where you think it comes from. The first question for all of these like scintillation-based, like Cherenkov radiation-based detectors is to answer whether this is really a cosmic neutrino. And there was a large and extensive and very conservative check performed, and no matter how you put it, like even if the direction was determined with a large error of several degrees, it's still the path through the water and through the rock is way too long for muons. It's like at the very least is around like 50 kilometers, and this means it cannot be an atmospheric muon, and it also cannot be atmospheric neutrinos, because the atmospheric neutrino flux, its spectrum, it's really well known. You don't expect like ever in many like thousands of years to detect at least even one atmospheric neutrino at these energies. So there's basically a very high confidence that this is a cosmic neutrino. I guess then what remains is just to find where it comes from, and this is the hard part with these neutrino detectors. It's the hard part because, like, you can imagine from all of these photomultipliers and from reconstruction, you still have some just fundamental statistical uncertainty from where it comes from, and there is also like systematic uncertainty due to not knowing fully like the light propagation laws, like to the in the water, and the locations of each string. It also has some uncertainty, fundamental uncertainty. So even for the best events like this, the angular uncertainty is still in the range of like degree or degrees. That's why it's not trivial to tell whether it's associated with some known astrophysical source or not. There was actually an XTCD almost a month ago about this specific event. So highlighting how difficult, so the inherent difficulty of distinguishing flares from different sources. So it's like maybe it was a bioluminescent fish, but no, it was traveling the speed of light, so it cannot be undersea life. So I think it is again. So it's clear that it's cosmic neutrino. It just remains to see what it comes from. So yeah, actually a bit more details about energy, and so as I said, the angular uncertainty is 3 degrees. It's also pretty conservative here because it's like the came that like all kinds of systematic uncertainty everyone can think of, and edit a little bit on top of that, just to be certain that we don't and don't cut it out too quickly. So in the energy, of course, it's also pretty hard to measure because you can try to measure the muon energy, but muon also emits some light outside of the detector. So especially the upper limits on the energies from muon and from neutrinos, they are very loose, really. But still, like these are either 90 or 95% region. So we are pretty confident that the neutrino is at least around 100 peta-electron volts. And this is higher than everything that was observed before. I think at the very least, like 10 times higher. So this is really like, if you see a particle that is 10 times more energetic than before, it may even come from different processes. It's like a whole order of magnitude, or at the very least different source populations. So where it fits in the overall neutrino landscape, because the neutrino observatory, neutrino astronomy has been developing in the past decade, especially. And what you see here are some measurements from earlier studies, mostly with IceCube at lower energies, where you see, significant neutrino fluxes. It was reliably detected years ago. And then there are like population-based upper limits from earlier observations here. And this cross indicates the implied neutrino flux. Basically, the location of the cross is if you detect one neutrino on average per lifetime of KM3net. But I mean, if you only detect one neutrino, you don't know if it's like one per year or one per like 100 years, for example. So there are very large error bars, as as always happens with the single source. So it is consistent as a slight upper fluctuation from some neutrino flux. So it's not like fully against like what's previously known. And I guess these events are so rare, and we expect them to be very rare. So we are likely to see even one with all the combined exposure of KM3net, IceCube, and earlier telescopes like Antares that was also in the training. So events like these, even though they are rare, they help us. They are crucial to constrain the extremely high energy neutrino flux, and you cannot just extrapolate from lower energies. And now moving to the discussion of origins. Just to preface it with, we don't really know yet. There are several hypotheses. Some of them are more likely, some are less likely, but and some are probably infeasible. But there are several feasible hypotheses remain, and it's hard to really pin them down even further. So the first thoughts, of course, is okay. The event is like about 10 degrees from the galactic plane, so pretty close, and in some region with interesting gamma ray emission. So maybe it has a galactic origin. There was a dedicated paper. So there was this like Nature paper announcing the event itself, and there were several companion papers on the on different potential astrophysical explanations. So first, if it is a galactic source, is it a galactic diffuse emission? Basically, diffuse emission is you have cosmic rays traveling through our galaxy, and they sometimes interact with protons in our galaxy, and they have to produce some neutrino. And basically, all kinds of reasonable galactic diffuse models are here, and it doesn't even fit here on the plot, but they are orders of magnitude lower than even the strongest fluctuations from these observed neutrinos. So it's highly unlikely. It's probably infeasible, even if we twist our, even if we relax our knowledge of our understanding of galactic matter and cosmic rays in our galaxy. It probably doesn't look feasible to produce it with this mechanism. And then in the galaxy, we can have also point sources of neutrinos. And to produce neutrinos, you need, like, in our galaxy, probably you need gas that will provide the cold protons, and you need particle accelerators that provide ultra-relativistic protons. There are several hypotheses. None of them are really like detected, reliably detected as neutrino sources, even at lower energies. But there are several potential models. Maybe basically the question is always where do you accelerate these particles? And it can be like microquasars. It is effectively the same as AGN, just much smaller and much more local to us. It may be some shocks around supernova or in star clusters. You can do all kinds of stuff, but these energies. So first and foremost, even if we had some of these like brightest, most powerful sources of this kind very close to the event direction, it will still be at the very edge of what is feasible. If you twist the existing models a little bit, you can in principle probably get like to tens of petelectron volts sometimes. But here there was no like clear bright galactic source nearby. This is a plot from the galactic counterparts paper. There are only two stellar clusters there that are not really extreme in any sense within the error uncertainty, within the event uncertainty. And the conclusion in that study was that okay, it's also very unlikely that it comes from a galactic point source, at least given what we know about these kind of sources. So if it's not galaxies, then it has to be extragalactic. Again, let's start with point sources. So there are several realistic extragalactic sources that can accelerate protons to tens or higher of petelectron volts. This can be gamma ray bursts, tidal disruption events have been proposed, and all kinds of agents, either beamed like blazar or unbeamed but more nearby. But generally, it is feasible. With GRBs, I guess it's typically the easiest to rule out because you expect some very tight time coincidence, and there was no known GRB anywhere close in time. So most certainly it's not a GRB. With TDEs, it's of course not as straightforward as GRB because the scales are much long, time scales are much longer, and we probably have a much less complete sample of TDEs than of GRBs. But still, I mean, at these extreme energies, you generally expect something extreme happening at the source, and there was no known, at least there is no known TDE that would coincide with this event and roughly the same year or something. So probably it's also not a TDE. I think the first batch of papers, there was no like indicated paper studying these two hypotheses. It's just kind of considered generally unlikely. For AGN, the situation is more complicated. Of course, like we know thousands, millions probably of AGNs in the sky. And we know that they are generally efficient particle accelerators. AGNs and blazars specifically, and Seyfert galaxies, they are already known to be neutrino sources at lower energies, or at telectron volts. So it's kind of reasonable to look at them at higher energies as well. Still, these energies, they are kind of like several orders of magnitude higher than telectron volts, and they can be challenging to produce it. So these protons can be challenging to accelerate even for AGNs. So what did we do in the blazar's counterpart paper? We tried to make a kind of complete study of all these blazars in the error region. So this is the 3-degree circle, the event localization uncertainty, and we selected blazars with different kinds of methods. So I'm mostly a fan of radio field gas selection. I think it's especially for blazars. This is probably the most direct way, the most direct observational way to select blazars, and there's basically no other, almost no other way to produce bright compact radio emission. We know field gas samples pretty well, but we also used other like gamma ray blazars from Fermilab and two multivalence catalogs. And of course, in any 3-degree circle in the sky, you will have a lot of blazars. Here we found 17. They seem to be in the right part of this, only in the right part of this circle, but this doesn't seem to be like just any observational bias fundamentally, because at least in radio, we see some sources here, in gamma ray we see some source here, so it's probably not an observation bias, it's just something else, just a coincidence. And And we tried to look at them. Maybe like one of these blazars has something that will clearly point towards the neutrino coincidence. We didn't find a very strong, very surprising, very strong coincidences here. But we just highlight 3 of these sources. Maybe if this neutrino comes from a blazar, I guess most likely it comes from either of these 3. So first, it was the brightest in radio. It is, I think it is number 6. So it was brightest in radio. It had also some flaring behavior in gamma rays. Nothing too extreme though. But generally, like if it is very strong in the radio, this indicates a strong jet beaming and small viewing angles that can be that can affect neutrinos as well. The second one must be number 8. It had it's also reasonably bright in radio, and it had a radio flare within actually that peaked within 5 days of the neutrino arrival. This is a little bit less common. I think the just chance to see such close flare coincidence is less than 1% in any 3-degree region, but still it's possible. So we don't claim this as a coincidence either. But I didn't expect to see such a close coincidence in time. And the last one is just closest to the center of this uncertainty region, and it had some flaring behavior in X-rays. Although, as you can see, there are only a few points, and we really don't know what happened to it outside of this time window. There is no clear evidence of either of these sources being the origin of the high-energy neutrino, but at least it's generally feasible. So regarding the feasibility, the main question, the main complication here is that to produce even, so for us to detect even 1 neutrino per 1,000 years from some source, for a typical blazer, duration around 1, and if beaming, jet line beaming, if it enhances emission by a factor of 1,000, this is typical for electromagnetic emission. Maybe it's typical for neutrinos as well. We don't know for certain. But even under these conditions, you still need proton power of 10 to the 45 erg per second, and this is not the total proton power. It's really the power in these extremely high energy protons of hundreds of petaelectron volts. And the 10 to the 45 ergs per second is already a significant fraction of the overall jet energy. And if we have high energy protons, we probably have much more of lower energy protons. So it's kind of the power tensions are still there. Also, it's kind of like by tweaking the acceleration mechanism of this can be made close to realistic. Like maybe it's not 1 neutrino per source per 100 years. Maybe it's 1 neutrino per source per 100,000 years. And maybe the proton spectrum is not the accelerated proton spectrum is not very wide. It's somehow concentrated at petaelectron volt energies, meaning that the total proton power is not much more than the proton power in the highest energies. This I guess leaves questions onto what are the potential proton acceleration mechanisms in blazars. Can they produce extremely energetic protons with a reasonably narrow spectrum that doesn't go like 5-10 orders of magnitude down, but it's kind of close to being realistic. We definitely cannot rule out the AGN blazar explanation. And the last one, so basically we discussed the diffuse and point source galactic emissions, and we discussed the point source extragalactic emission. So cosmogenic origins, it's a diffuse extragalactic emission. Cosmogenic just means that it's an interaction of cosmic rays that we know they exist, and they just don't reach Earth from very distant sources because they interact with CMB or other photon fields, or maybe even matter fields, but I guess most likely protons, photon fields. And we generally know the spectrum of cosmic rays, at least on Earth. And there are, of course, like always these assumptions, like how do you extrapolate the spectrum that we observe on Earth, how they extrapolate it to the whole universe. There is probably some evolution and so on. So there is, of course, this cosmogenic neutrino spectrum is definitely not well known or well measured or constrained. And these are some plots. So here it's the same cross for the infinite neutrino detection and inferred neutrino fluxes. And these lines, these colored lines, they represent different models, different source evolution, different redshift cutoffs, and some other parameters of the cosmogenic neutrino production models. And for some of the more extreme models, like you see, there are some yellow lines here. Maybe they're not the most maybe they don't have the highest contrast here. But it's generally feasible for this event to be like a slight upward fluctuation from this kind of flux. So personally, I think it is very feasible, and this was also the conclusion in the companion paper on cosmogenic origins. This scenario, as it is diffuse, it's very hard to constrain or allow. I guess in the future, process will go like we will try to check point source hypothesis more directly, and if no point source hypothesis works, I guess this kind of like diffuse extragalactic emission is the only thing that remains. But for cosmic rays from cosmological distances, there are no other observational traces known. We cannot detect these cosmic rays directly. So this is a hard question how to constrain this model, I guess, only looking at the spectrum consistency and other point source explanations. Basically, to sum it up, this neutrino was detected in the instrument 2 years ago. It was announced about a month ago because of all the cross checks and paper publication, paper review time. This is an extremely high energy neutrino. So if you take the best fit neutrino model of 220 petaelectron volts, it's about 30 times higher than the next highest energy neutrino ever detected. But I mean, maybe it's not 200, maybe it's less than 100. It's still much higher than the next highest. These events are very rare. We are likely to get even one among all the combined exposure of neutrino telescopes, including ChemSerenade, IceCube, Baikal GVD. As of now, among the considered and evaluated hypotheses, we have two realistic ones that can't be ruled out yet. It's a blazer. This neutrino comes from blazers, or it comes from cosmic ray interactions with intergalactic fields, photon or matter. For this specific event, we expect some modest direction reconstruction improvements, probably later this year. It won't get 3 degrees down to like half a degree, but maybe to like 2 degrees, and we'll see whether it will move it away from this from the brightest blazers, or it move it closer to them. We will see how it goes. And of course, in the future, with growing neutrino detectors, and especially like there are several planned detectors that will cover even larger areas, larger volumes of the ice with radio Cherenkov detectors. So basically, have radio antennas that point towards the ice and measure Cherenkov radiation. It is easier to cover larger areas. That is more useful to detect extremely high energy neutrinos than the current telescope. So we are really looking for this kind of improvement. And this is almost it. And just for a slight technical comment, I'm happy to see the Joomla language being used more and more. We use it a lot in the Black Hole Initiative and the Event Horizon Telescope. It's also used more and more in the Chem3Net. It was used for some event reconstruction, like for these kind of plots that they were made in Julia. And so I was the corresponding author of the Blazer counterpart paper. We did most of the analysis in Julia as well, and most of the plots. So, yeah. So I'll leave it and happy to answer any questions or discuss anything related. Thank you.
you look at the polymer source of your blazon, you need to handle your blazon. So things that she has one trait of a blazon behavior, but are not being confirmed to the blazer, thanks to gamma radiation, radio observations, or variability.
So then the question is like, what is a trait of a blazer, right? So if by blazer you mean, so generally I personally, when I say blazer, I mean an AGN with a like bright, powerful jet that is pointing towards us. That's basically it. And for this purpose, I think radio observations are a pretty clean way to select them. So like we know that not all blazers are gamma ray bright, so we don't expect all of them to pop up as Fermi sources. So I know that BusyCat, their aim is to have a clean catalog, not necessarily complete. So basically, almost everything that is in BusyCat is a blazer. It was like checked spectroscopically and everything, but it's by far not complete. It's not the goal. This part, it was kind of like a bit ad hoc cross match with like basically what you say. If you see consistent blazer properties and like in several bands, then it's also more likely to be a blazer. I think the two kind of just direct observational selections are the radio and the gamma rays here. So in radio, we just do a basically cutoff by flux and spectrum of the compact emission, and this is pretty reliable, I think. Depending on, of course, where you put the cutoff, but it selects a lot of lasers. So yeah, these are the most direct observation ones.
Any other questions?
So this would be well within the capability of IceCube to detect, right? By chance, that's the dotted line is the sensitivity of IceCube.
It's the upper limit. Yeah. This means that the flux is the actual neutrino flux is probably below this line. Yes. With one neutrino and with for sources, it's called the Eddington bias, but generally, if you see one particle at these energies, it's hard to tell what the flux is. It can be like one particle per like 10 exposures, for example. And it was kind of similar to the first high energy, like first pentaelectron fold energies neutrinos with IceCube. I think there was like also almost an order of magnitude gap between like it was like one neutrino at 6 PeV, and others were like around PeV or less for quite some time. Now I think there's something intermediate, but yeah, there's just a large gap until the next highest energy detected neutrino. So these are kind of also have some assumptions, but I think these upper limits are pretty reliable.
So there's plans to increase the size of IceCube substantially.
It's at these highest energies, it's not just the size of IceCube, there is IceCube Gen 2, I think it's not, and the part of the generation 2 will be the radio array that will cover a larger volume. And there is also like planned like telescope being designed on the same matter in Greenland as well, in Greenland ice, and maybe somewhere else. So there will be, assuming they get funding and they get built, there will be several of these like detectors much more best suitable for these highest energy neutrinos, because like for highest energy neutrinos, you really need higher volume. You don't need to instrument it as densely as for lower energies. So we'll see.
Any other questions?
Yeah, thanks. That's a fascinating event and great talk. Thanks. Apologies for the cheeky question. What would happen if the neutrino interacted in this room? Would we recognize it? Would we see a flash of light, or is it too fast? Or
so if it interacts, the neutrinos barely interact with water. I think it's some column density to the first order. It's kind of proportional to mass, I guess. So they can interact in water, much less so in the air. And when they interact, they produce muons, and these muons produce these like Cherenkov radiation. But the reason why it's possible to be detected is because it's very dark.
sure.
So here, even if it was filled with water, we probably wouldn't see anything.
Any other questions? Okay, so I have a few questions. So do magnetars and FRBs, have they been considered? And then secondly, can you explain how the TD microtubes and ultra high energy.
So these are, I guess, two kind of different questions. First, I go about magnetars that presumably are talking about galactic magnetars. So you need like not just bright emission, like photon emission, like radio or optical. You need also some particle acceleration. I think regarding pulsars, it's mostly there with nebulae and is I guess pulsar like on these fronts. This is feasible to accelerate. It's like extremely hard to get to repel electron and for example, now the galactic neutrinos were detected at lower energies besides field and like TeV energies, and there is still like a large question whether it's diffuse flux, whether it's point sources or something like that, because at these energies you have a lot of background and statistical problems. Regarding FRBs, I think here it's the same situation as with GRBs, because you expect random pretty close speeds at the same time. And for this specific event, I don't think we even looked at the FRB catalog, so it can be an easy cross check. I guess someone looked actually. I mean, there were already several papers from outside of the collaboration in the first few days. But for other like lower energy neutrinos, there have been no hint for them being correlated to FRBs. These were definitely done at lower energies, where you have like at least tens of neutrinos or about 100. It was done. There is like really no correlation with FRBs. It's also easy to rule out because you need a reasonable time coincidence. Regarding TD, so the thing is the tidal destruction event, if it happens next to a supermassive black hole, it forms a jet. The jet is temporary. But the physics there are about the same as in persistent jets in AGNs. They can be actually surprisingly similar. They can have the same similar powers, maybe sometimes even higher instantaneous powers. They accelerate at least electrons to similar energies as AGN jets. They are similarly beamed. They are just temporary. So TD is it's the same physics as AGN or laser jets. It's just temporary.
Any final questions? So with that, let's thank Sasha again.
Thank you.